Hi there, I'm going to show you the impact of component Q factor on a very steep LC filter. I'll also show you how to measure the Q factor of those components with a nano VNA. Let's get started. So what is Q factor? Q factor is basically unwanted loss. So I've drawn an inductor here and a capacitor, and normally the only thing you would want is this inductive element. However, in practice you get a loss element in series with it, and that's going to degrade the performance. Now, high Q means low loss and low Q means high loss, just to keep it confusing. So with the high Q, these loss resistors will be very, very small. So you may wonder where this loss comes from. In an inductor, it's either the resistance of the wire, which makes up the inductor, or it's the core material. And in a capacitor, it's usually the dielectric that has a loss factor. So this is the filter circuit I'll be using. Some of you may know it from previous videos. It's a 9th order elliptical 30 MHz filter, and it has a very steep response. So it's very flat up to 30 MHz and then it drops down like a brick. And here you can see the actual filter board. You have the in and the output connector, 1, 2, 3, 4 inductors, and the rest are all capacitors. So for the inductors, I have several options. I have 2 off-the-shelf options and I have 2 hand-wound options that I want to show. Unfortunately, the hand-wound options I can't put on the board because they get so close together that they start talking to each other electromagnetically, and that means that the filter doesn't work. Now for the 2 standard options, I have an air core version and a ferrite core version. They both are the same value, just they have a vastly different Q factor. The air core has a Q factor of 80, which is of course very good. Higher Q means better. And a ferrite core has a lower Q factor of 40, which is worse. I've also stated the DC resistance here. So that's basically the DC resistance of the wires that make up the inductor. And the resonance frequency. I don't want to go that much into the resonance frequency, but basically it's the frequency where the inductor turns into a capacitor. Yeah, you got that right. Inductors can behave like capacitors. But that's something more for another movie to get into more detail. Another thing I need to mention is that these air core inductors were the best that I could find off the shelf at DigiKey, so that's why I chose these. So let's get to the measurements. For the measurements I'm using my trusty nano VNA, which I've got connected to a computer, and I do the data processing in Python. Now these are the measurement results for the passband, and you see here exactly what you expect. So the light blue line is the ideal simulation that I did with Schematics. The purple line is what you get with low loss, high Q air core inductors, and the yellow line is what you get with lower Q ferrite inductors. So you clearly see that if you want really good performance, you really need a high Q factor. Now let's have a look at the wideband response. Here on the left top you see the characteristic difference again, and overall they're pretty much equal in the stop band. You can see here that the ferrite inductors are a little bit worse in this area. That's probably because we're above 165 MHz, where the ferrites stop acting like inductors. But then at 600 MHz we see that they're on top of each other again. The air core inductors act like inductors up till 600 MHz. Now there's one weird thing going on. This is the start of the stop band, so let me point that out. That's this area. And what you would expect is the air core inductors to be better than the ferrite core inductors. They have higher Q, so you expect these dips to be higher. You can see in the simulation, if your Q is infinite, then those dips will be very deep. So I think there's something like crosstalk going on between those air core inductors because their fields spread out wider. I'm not sure about this. This is just my theory. So let's see how we can measure the Q factor. This is the setup I'm going to use. I'm going to put a parallel resonator right in between the 2 ports of a nano VNA. And this will result in a dip. At the resonance point, in theory, a parallel resonator has an infinite impedance. Now the losses prevent it from having an infinite impedance, basically the Q factor. So this is the dip that you actually get. And this is the setup. I'm using a transmission line. I cut a hole in the transmission line and put the inductor and the capacitor across that hole, basically creating a parallel resonator. Now this is the simulation schematic. So we have the parallel resonator here with its loss resistance. And you have the 50 ohm source and the 50 ohm load. Now I use the schematic for simulation, so I can check if all my calculations are correct, and for calculations. Now let's see, how can we determine the Q factor of this resonator circuit based on the depth of the dip. You saw the dip in that previous picture. The depth of it can be used to calculate what this value of this resistor is, and that can be used to calculate the Q factor. So now the first thing we need to do is to convert that gain in decibels of that dip to a linear scale. So you do that by taking the 10 to the power of the gain in decibels divided by 20. I'll get to this divide by 2 in a second. Next, we need to calculate Rx based on that. Now, at the resonance point, the capacitor and the inductor are basically gone. So we're left with a resistive divider with 50 ohm, an unknown resistor, and a 50 ohm load. So we can also say 50 ohm is Z0. So the gain is basically the ratio between this resistor here and these two added together. So we can convert that to Rx is Z0 times, well, you can read it here. Now, where does the divide by 2 come from? The nano VNA will assume that you have 6 dBs of loss because you have a 50 ohm source and a 50 ohm load, and it deals with that, it corrects for that. However, in this schematic, we get a 6 dB loss because in the ideal case, this is 50 ohm, Rx is 0, this is 50 ohm, these are gone, so you have half your signal, so that's 6 dB. So in order to correct for that, we have to divide this gain by 2. Now the final step is to calculate the Q. Now calculating the Q of a parallel resonator is very easy once you know all the component values. You just multiply Rx with the square root of C divided by L. If you want to become an electronic specialist yourself, you can download my free product development checklist. It contains all my knowledge from 30 years of being an electronics professional and 42 years of being a hobbyist, and the focus is on how to get your electronic product right the first time. You can also watch all my videos for free. Now, I've also started development of a professional course that is not for free. This will broadly be based on my free product development checklist, and it will be the hands-on development of a pretty complex board. And I'm really enthusiastic about it. This is actually going to be a great course that's really going to boost your electronics knowledge. Let's continue. So let's have a look at the measurement results. I have 3 different situations. I use the air core conductor in combination with X7R capacitors, which should be worse than NP0 or COG capacitors. I used the air core in combination with NP0 capacitors, and I used the ferrite core with NP0 capacitors, and all ended up around 70, which is a little bit strange because the ferrite core was supposed to be worse, but we'll get to that in a moment. Now you can see that NP0 and X7R don't really make a lot of difference here. X7R should be far worse than NP0, so apparently the inductor is the limiting factor here. Now let's see how you can calculate this. I've already given you the formulas a little while back, and now I'm just going to show you a calculation example. So we got minus 37 dB, so that's what we fill in here for the GdB, and if we calculate that, we get a gain of 0.00706. Now we can plug that into the next formula to calculate Rx, which is 6980 ohms. We plug in the gain in 2 locations and calculate it. And after that we can calculate the Q, which gets to 69.8. So that's roughly equal to the 70 that I just showed in that diagram. Now I already mentioned it's a little bit weird that this ferrite core had a Q of 70 equal to the air core. So I wondered, in the datasheet it said it was minimum of 40 at 25 megahertz. So I reduced the resonance frequency to 25 megahertz, and I did that by adding 100 picofarad. So it's 133 pico plus 330 nanos. And what we see is we get minus 31 dB as a dip, and the Q is 66. So where they're stating that it's a minimum 40, they're being very, very generous with their Q because you're actually getting 66. Another thing that's good to realize is that the Q factor of an inductor is never constant versus frequency. On this graph, you see the Q factor versus frequency for a Coilcraft inductor series, and you see how it varies from basically 0 at 1 megahertz up to something like 220 at something like 600 megahertz. By the way, these are incredibly good coils. So this explains why we got different Q factor values at different frequencies in the measurements. So I was curious, would I be able to make something better myself? So I made 2 air core inductors. So the first one I made is this one, and it's basically a 3D printed coil former where I put on windings. When I measured it, I got to a Q of 70, and I was a little bit disappointed why this was so low. So I did some research and I asked ChatGPT, believe it or not, on the parameters that make a high Q inductor. And it said, well, use a larger loop and space the windings a little bit further. So as you can see, I made this bigger one, which has a larger loop and wider spaced windings. And you see that the Q is 125. Now this is quite impressive. So you might be wondering, how did I come up with the dimensions for these inductors? And it's very simple. If you go to Google and you type in air core inductor calculator, you get countless links of people who've put calculators on the web. What I notice is the value is not always very accurate. So you get a good starting point and then you have to either add a few windings or remove a few windings. So you need a way to measure it. Well, the nano VNA, turning it into a resonator, is a great way to measure the value. But yeah, that's basically how I got the parameters for these inductors. Now, as I was filming this board was delivered to my house, and this is the board that I'll be using for my coming 4 or 5 YouTube videos. It's all RF building blocks. It contains a red race ring at 1.5 gigahertz, a 2-stage Wilkinson combiner at 1.5 gigahertz, a 20 dB 1.5 gigahertz coupler, directional coupler, a bunch of quarter wave transformers, single stage, double stage and triple stage, a 90-degree hybrid, and an extreme return current experiment. So yeah, wait for this the coming months. I'll be making videos on this. I'll show you how to design these things. And yeah, then you can design these things yourself at home as well. I hope you enjoyed this video again, and see you next time.